Let us write down the Reynolds transport equation in general once again before going into the conservation of momentum. So if we have a control volume which moves with a velocity b, if we have a control volume which moves with a velocity b, then the equation is written as ddt of integral of f over the control volume is equal to integral of del f del t dv plus integral f b dot n dA over the surface area. So when the so the important point to note here is that the velocity b can be non-local. It need not be confined to the being a uniform velocity all over the surface. So b can vary locally. All right. So when b is equal to the velocity of the fluid, then this particular chunk of fluid which we have identified, which is essentially the control mass, so the chunk of fluid moves with the fluid, meaning it is advected exactly as the fluid would move. The control volume is not having a velocity which is separate from the fluid velocity. And if the chunk of fluid moves with the fluid, then it means that the acceleration encountered by this chunk of fluid is because of all the forces acting on the fluid itself. Okay, so ddt of integral f dv in a frame which moves with the fluid velocity is equal to integral del f del t dv plus f u dot n dA. And in order to make this equation as a momentum conservation equation, we must replace f by the momentum per unit volume. And so the momentum per unit volume of this fluid chunk is going to be rho times its velocity. So therefore, the term can be written as ddt of integral rho u dv is equal to integral del t of rho u plus integral rho u dot n dA. Here, essentially, this equation has three components. It is not an equation which only has one component because it's momentum. So if you were to write things down, the three components, let me just write down the first component. So the first component would be rho u dv, where it is the u component, is equal to del t of rho u plus integral rho u, but it will still be u dot n dA. So this particular term is the entity being carried by this flux. So it is still going to be a vector flux, but this is the entity being carried by the vector flux, which is the x momentum. So this is the x momentum. All right. So if I were to draw an area like this, so suppose the velocity goes something like this. This is the area vector. So the flux going through this surface is u dot n, no doubt. And what are the momentum components of this flux? It will be u dot I. This is the x momentum. So you are splitting the velocity at this point. So suppose this is the x direction, this is the I direction, this is the j direction, and this is the k direction. So u dot I is the x sort of momentum, I mean the velocity component of velocity in the x direction, u dot j and u dot k will be the y and z components. So these are sort of, so rho times this is the sort of momentum per unit volume. So this is the x momentum per volume, y and z, and the flux which carries this momentum is this. So this will not be broken up into its component, but it will still be u dot n cap. I hope this particular concept is clear, and if not, it will be clearer through the examples that we will do. So now if the fluid is moving with if the control mass is moving with the velocity of the fluid, the left hand side we have already seen is this particular term, and on the right hand side, what causes this rate of change of momentum? Okay, the cause of the rate of change of momentum, and that cause is the summation of all the forces, and the forces for a fluid can be broken down into F body and F surface. So there are two kinds of forces which can act on a material volume. The first one is called as the body force, and the second one is called as a surface force. A body force is something which acts on the entire volume of the liquid. And this can include forces such as the force due to gravity, electromagnetic forces. I mean, it's not general, but electromagnetic forces can act at the interface also. But so suppose you have a charged fluid which has a charge density of Q. So if you put an electric field here, so the force will be proportional to the total charge. So it will be Q times E. Okay. So the body force can be electromagnetic in nature, it can be magnetic in nature, it can be thermal in nature. So if you have a heating over here, so the entire fluid sort of experiences a buoyancy. So this kind of flow is called as convective flows. Okay, so it can be thermal in nature. So there can be various uh, phenomena which can give rise to the occurrence of a body force, and a body force can therefore be represented as integral rho times some acceleration due to that body force times dv. So this, when integrated, is like the acceleration acting over the total mass, and in the case of gravity only, it will be equal to g. In the case of gravity, it will be only g. So the body force due to gravity, so Fb due to gravity is equal to integral rho g dv. And if we take a Cartesian system where z is pointing upwards, then obviously the z component of the momentum equation will contain a term minus rho g dv. So see, the momentum equation, we had three terms. So the first term of this is 0, the second term of this, so this is in the x direction, this is in the y direction. In the z direction you will have minus integral rho g dv, where this g is now a scalar, this g was a vector. Alright, so the three components you have to match with these three body forces. Now body forces can also be conservative and non-conservative in nature. A conservative body force means that, or rather, a conservative force implies that the force can be written as the negative of a potential. Okay, so in the case of gravity, we can write, so let this be the force per unit volume. So small f, rho times g is equal to minus grad phi. So the phi which satisfies this is rho minus rho gz. Okay, so this is like the potential. This is like the potential. So a conservative force field gives rise to a force which is the minus of the gradient of the potential, and the advantage is it just depends on the endpoints. The force acting just depends on the endpoints and not the path. As a non-conservative, it is path dependent, and I think you have studied such things in your class 12. So whenever it is required, we will make use of this fact, but as of now we don't really need it. So now we come to the description of surface forces. So fluid elements, as we have studied, are, are rubbing against other fluid elements. I mean, I'm drawing cubes, but in general there are different volumes. But the point is, the force between two fluid elements, or in fact between acting on a fluid element, can be transmitted through the traction vector. So this is the traction vector, and we have studied this in the very beginning. And the traction vector is a vector, so it is the surface force, let me call it Fs. We had found out that it can be related to the Cartesian components of the stress tensor, or rather it can be related to the stress tensor. So the traction vector on an area which has a normal vector n, we had obtained was equal to the stress tensor dot the n, or rather in index notation Fi or Fj was tau ij ni. Okay, so this is the way to write it, and this should be transpose, but tau transpose is equal to tau. As we had already seen, the stress tensor is a symmetric tensor. And why is a stress tensor symmetric? You can recall from solid mechanics, if I take a cubic element like this, if this is tau 1 1, this is tau 1 2, this will be tau 2 1, this is tau 2 2, and so on. If I take the moment along this point, right, if I take a moment about this point, one will obtain tau 1 2 minus tau 2 1 is equal to the net moment. And fluid elements, under normal circumstances, do not have a net moment, and thus it will be 0, rather moment per unit distance. So if this distance is t, but anyway, so if a fluid element has no moment, then tau 1 2 is equal to tau 2 1, and you might have done this in your solid mechanics course as well, or other mechanics course as well. So because of this, tau transpose dot n cap is the same as tau dot n cap, and hence we can write this statement, no problem. So the more important thing is, when is this not equal? When is this condition not fulfilled? In the case of ferrofluids, which are basically small pilings of iron suspended in water or some other solvent, they have a net moment. There are various other, but they are very specialized cases, and in general, tau 1 2 is equal to tau 2. If not, then you have to decompose tau into its symmetric component, antisymmetric component, and do the entire mathematics. Alright, so the traction vector can be related to the stress like this, but for now let us keep it in terms of the traction vector. So far we have seen the existence of a traction vector. So traction vector, when you integrate it over the entire surface, it gives you the total force because of this particular surface force. So let us compile the things that we have studied so far. So integral del T of rho u plus rho u dv plus integral rho u dot n dA is equal to, so the first term is the body force and the second term is the traction, the surface force. Okay, and there is one other particular kind of force. It is called as the interfacial force. So forces such as surface tension, other kinds of electromagnetic interactions, they are manifesting at the interface of liquid 1 and liquid 2, or fluid 1 and fluid 2. It can be air water interface also. So these kind of interfacial forces are typically not in the conservation equation, but they manifest themselves in the boundary conditions. They do not manifest themselves in the Gurney equation because they are not occurring inside a point in the domain. They are only occurring at the interface. So the way to find out those boundary conditions, in fact, is to take an interface, make a pillbox, and apply this conservation equation at this point, and then account for the force acting at the interface and let this shrink. So let delta z go to 0. But I'm just giving you an outline. I mean, if we get the chance, we can discuss it in greater detail. So let me just copy this. Okay. Huh, not pasting anymore. Just try one last time. Okay, I'll just write it down. So del T rho u dv plus integral rho u dot n dA is equal to integral rho g dv plus f dA. So this is the momentum equation for a control volume moving with the fluid. Now if I want to apply this to any general control volume moving with an arbitrary velocity, so how can I do that? So the first thing to note is ddt of integral rho u dv is equal to del T of rho u dv plus integral rho u b dot n dA. So this is the flux caused by the moving control volume which has a velocity b and not the velocity of the fluid. Now I will call this as v star and this is a star. We can make this arbitrary control volume coincide. So this is the arbitrary control volume and this is the actual control volume. We can make them coincide at a given point in time, which means that integral del T of rho u dv will be equal regardless of which volume you are selecting, either this or this, but the other terms will be different. This term will be different than this. I mean, of course that is different, but this term will be different, this term will be different. So basically you are making the volumes coincide for that particular time instant, and thus we can write down an expression. So basically this particular term is equal to this particular term. So if we substitute this over here, or sorry, this is not equal, this particular term is equal to this particular term, my bad. So the time derivatives are equal. Okay. So in this case, if they are equal, I can substitute this expression over here. So this expression is equal to this minus of this. So I have ddt of integral rho u dv minus integral rho u b dot n dA plus integral rho u dot n dA is equal to integral rho g dv plus integral f dA, and thus we can combine these two terms and we can write ddt of integral rho u dv plus integral rho u minus b dot n dA is equal to integral rho g dv plus integral f dA. The physical meaning of this particular term is clear. So if I have a surface which is moving with a velocity b, and if the fluid moves with a velocity u, then the relative flux of this fluid coming out will be u minus b dot n dA. So this is like the relative flux and relative to the moving control volume. So now if the area is moving with the velocity v, velocity u, then you have no flux coming out, and essentially there will be no momentum flux also. So momentum flux can exist across a surface. Okay, listen to me carefully. Momentum flux can exist across a surface if there is some flux crossing that surface. And if flux crosses at all, then the flux taken out by that, the momentum taken out by that flux will be equal to the individual components of the velocity. So this is what it all means. Okay. Okay. Any doubt in this so far?
The last part, can you repeat momentum flux exist? Okay.
Pardon me.
The last part you told the momentum flux will only exist if flux across the surface exists. I didn't understand the statement.
So suppose you are okay. Suppose you have a fluid which is moving with 1 meter per second, and you have an area which is stationary, 0 meter per second. So how much flux is crossing this area? The flux crossing that area is equal to 1 times the area. Okay. But now suppose this particle is moving with 1 meter per second and it is able to cross this surface, and hence you have this particular flux. Now let me take another case where this particle which is just about to cross the surface, right? It is just about to cross the surface, but now the surface itself is moving with 1 meter per second. So the particle moves with 1 meter per second and the surface itself is moving with 1 meter per second. So that particle is never able to cross. So there is no flux. Now consider the case where the particle is moving with 1 meter per second, but the surface is moving with 0.5 meter per second. So per second, I will only have half the flux. So it will be 1 minus 0.5 times the area, that is the flux. But now this flux, whatever is coming out of the surface, will encompass a momentum of 1 meter per second, or rho times 1 meter per second. So that is the meaning of this. Okay. So in every conservation equation, whenever you have flux crossing a surface, you have to first find out how much flux is crossing that surface. And how much flux is crossing the surface is a function of the relative velocity of the velocity at that point to the area, the velocity of the area. It cannot be just the absolute velocity. And the flux being carried is equal to whatever momentum the liquid has. Okay. And let us look at some examples. I mean, despite this, I mean, it may feel a bit odd to learn all this, but when we do the examples, it will be abundantly clear, and I hope you will follow it with great attention. So let us go to our first example. Our first example is as follows. We have a uniform flow coming in from one side, and the flow velocity is u infinity, and there is a body which is kept in the middle. It looks like an I-beam. It can be anything. It can be a ball, I-beam, whatever. But the point is, it is very large into the depth. So lastly, we say that the velocity profile at the exit, it looks something like this. Because of the presence of the rod, the velocity over here is reduced, and because of, I mean, and very far from this, the velocity is once again u infinity. So this profile is u as a function of y. So this is the x direction and this is the y direction. So the question is, find out an expression for the drag acting on the body. So before going into this, let us quickly discuss the strategy we should have. So because of this deficit in momentum, so let us first understand the physics of it. Because of this deficit in the momentum, this object has applied certain force on the fluid. So if the object exerts a force on the fluid in this direction, so if the object puts a force on the fluid in this direction, then whatever the incoming momentum is will reduce, and it has reduced. It has become u as a function of y, where if it were to be undisturbed, this would be the velocity. So this much momentum the fluid has lost because of the force acting on the fluid in this direction. So this is the force on the fluid because of the object. So now if this is the case, the force on the object because of the fluid will be in this direction, and that is the drag. So if you try to keep your hand like this, I mean, this is your hand, a very nominal hand. If wind is coming in this direction, your hand will try to go in this direction, but of course you are very powerful, because of which you can keep your hand steady, right? So the drag on the object acts on the x direction, but the drag on the fluid acts in the opposite direction. So let us first draw the control volume like this. So this is the control volume. The control volume also excludes this object. So this green thing is the control volume. Momentum enters the control volume over here and momentum leaves the control volume over here. And the deficit in momentum is causing a net force on the object, which we are expected to find out. So first of all, let us do a mass conservation. Because the rationale is, if the velocity over here is u as a function of y, okay, the velocity at this point is u as a function of y, which is whose integral over this length is going to be less than the integral over this length of this velocity, and hence there has to be some mass which is coming out of this green control volume. Why? Because more mass is coming in than what is going out. Because of the reduced velocity over here, less mass is going out, and you should be able to convince yourself that if this is true, if this mass comes in, less mass goes out, there has to be some mass which has to come out of these faces as well. So this is the first step. So we have to first do the mass conservation. So let us write it down. So let us choose the control volume whose velocity is 0. So for this ddt of integral rho dv plus integral rho u minus b dot n dA equal to 0. This is the mass conservation equation. And because we are considering a steady flow, that is, this control volume is not deforming, neither is the mass inside. So this term will be 0 because it's a steady flow. B is equal to 0. So it essentially boils down to rho u dot n dA equal to 0. So now let us write down, let this be inlet face, let this be outlet face, let this be top, and let this be bottom. So integral rho u dot n dA inlet plus integral rho u dot n dA outlet plus rho u dot n dA up or the top plus integral rho u dot n dA at the bottom is equal to 0. Now at the inlet, u dot n, so u infinity is in this direction, n vector is in this direction, so u dot n will be minus, and this will be minus rho u infinity, or let us keep it in this integral form. What about the exit? It will be plus, so u y is in this direction, u as a function of y is in this direction, the n vector is also in that direction, so this will be rho u as a function of y dA. Plus, let us write these terms down. So it is rho u dot n cap dA on the up face plus rho u dot n dA on the bottom face. Now, what is the flux that is actually going to come out? We don't care. We just want to know that yes, there is some mass that is coming out. Now, why do I say that mass is coming out? I mean, obviously the physical reason is quite clear, that if net inlet is there, then there has to be some net outlet. So if there is some net outlet, then u dot n cap has to be positive. From the top and bottom surfaces, u dot n cap dA has to be positive. Now look, this u dot n cap for the top and bottom surface are these two terms. Now if I take whatever is on this side to the other side, integral rho u dot n dA up plus rho u dot n dA for the bottom is equal to integral rho u infinity minus u as a function of y dA. Okay, it is u, this minus will become positive on the other side, so it's rho u infinity minus u dA. And because u infinity is larger than u in over all the points in the domain, this is going to be positive term, and hence there is a net outflux from the control volume. So this is the very first step, and so far there should be no doubt in your mind about what you're doing. Let me copy this, and I hope it doesn't copy. I don't know what is wrong, but no problem. We'll just redraw the entire control volume. Okay, this is a very quick render of the control volume. This is u infinity. This is going to be u as a function of y. So we already have seen this. Let us write down the conservation of momentum equation for this. Okay. Let us write down the conservation of momentum for this. So the conservation of momentum is going to be ddt of integral rho u dv plus rho u minus b dot n vector dA, and it is equal to the net force acting on the control volume, and we've already discussed that the net force acting on the control volume is going to be in this direction, and that is going to be the drag force. So it's going to be minus fd in the x direction. Okay, and the control volume has a zero velocity, and the control volume is stationary, and the control volume is not deforming, and the control volume, the entire process is a steady process. So this time dependent term vanishes, this b vanishes, and finally we have this. Okay, so now let us write down again at the inlet, outlet, up and bottom. So in the inlet, what is rho u infinity? So let us write down the x momentum equation. Okay, we are writing down the, we want to find out the x momentum equation. So whatever u vector there is will be replaced by only u. So it will be rho u, but again this will be u dot n cap. So this for the inlet surface will be rho u infinity minus u infinity dA, and this minus u infinity is because u dot n cap, nothing else. So this is the x momentum being brought in through this particular surface. It is coming in through this particular surface. At the outlet, what will be this expression? It will be rho u as a function of y times u as a function of y dA. As simple as that. There's nothing complicated in this. What about the top surface and the bottom surface? It will be integral rho. Now what is the momentum being carried by the top and bottom surfaces, or rather what is the momentum carried by the flux which is coming out of the top and bottom surfaces? The momentum over here will be the flux coming out times the x velocity encountered at that surface. Okay, so the x velocity encountered at that surface is going to be u infinity, because we have drawn a large enough control volume so that the velocity at the edge of the control volume again becomes u infinity, as we had drawn in the very beginning. So it will be rho u infinity, but now this flux is still this. This is going to be top plus rho u infinity u dot n dA at the bottom. This particular term can be combined as u infinity integral rho u dot n dA top plus integral rho u dot n dA bottom. So essentially it is the flux, the mass flux that is coming out, it is the mass flux that is coming out from the top and bottom surface times the momentum component in the x direction, because we are writing down the momentum equation in the x direction. Alright, we're writing down the momentum equation in the x direction. So the various terms in the balance on the left hand side will be integral, this is minus rho u infinity square dA, this term is plus rho u as a function of y square dA plus u infinity times this mass flux, which is equal to this. It will be rho u infinity minus uy dA. I have substituted the fact that this entire term is the same as this entire term, which is equal to this term, and this will be equal to minus fd. I have dropped ex because we are writing down the momentum balance in the x direction, and hence it will be only fd. So what do we get? What do we on the left hand side? What do we have? So it's, so let's take a negative of all the terms. All right. So what do we have? we have integral rho u infinity square dA over this area minus integral rho uy square dA over this area, and the dy for, so dA is essentially dy multiplied by the length into the plane, and the length into the plane we can choose to be 1, or we can do the entire calculation per unit length, no problem. So essentially it's going to be dy times the length into the plane, okay, and this term is plus u infinity, or let me take this u infinity inside, so integral rho minus, so what is this going to be, minus u infinity square plus u infinity uy dA, and dA is again dy times length, this is going to be fd. So the force per unit length is equal to, and this integral is once again over this height only. We have converted the integral over these two areas to something which we know over these heights, okay. So this is going to be, so this rho u infinity square is going to cancel out, so it's going to be integral uy times u infinity minus uy dy over the height. So if I say is going from minus h by 2 to h by 2, okay, so this is the expression for the force acting per unit length on the object. So all you need to know, so what is the advantage of doing this? So all you need to know is what is the velocity profile at the outlet. I don't need to know whatever is going on inside. I just need to know what is the velocity field at the outlet. If I know that incoming velocity is uniform, I can find out the drag acting on the object. And the drag is obviously equal to the deficit of the velocity at the exit relative to the incoming velocity. This. Okay. Any doubt in this so far?
Sir,
Yeah?
so like, could you please slide up?
Yeah.
So here, rho vector u times vector u dot and dA is equal to minus fd ex.
Hmm.
At the top surface, vector u will be u infinity.
U infinity ex.
U
Vector.
infinity ex. And also at the top surface, vector n will be ey.
Yes.
And then vector u dot vector n at the top surface will
No,
be
okay.
0.
I'll tell you why that small issue is happening. I don't know who you are. What is your name?
Not sir.
Sheikh Mo. It's a very good question, first of all. And this kind of question, I am very happy to hear that you are paying deep attention to whatever is going on. Okay, so his question is very obvious, that these surfaces are having an n vector like this, and my claim is that the velocity is in this direction. So u dot n cap is 0. So what's going on? And the answer is as follows. This profile is something like this. Okay. The profile over here is something like this, and it is like a deficit in the incoming velocity. Whatever there is deficit coming in, you are sort of trying to find it out. And we've seen that a deficit in the incoming velocity will give rise to some velocity flux like this. Now this velocity flux implies that the velocity at this point is not u infinity ex. It is this u infinity ex plus some velocity v in ey direction. Okay. If this is true, then the flux is still integral v dot n dA as per this, and it will be, so v dot n cap over here will be simply v dx times the unit length, and now the momentum being carried by this flux is this, but the x component of that momentum is only going to be this. So hence the momentum being carried will be rho u infinity times v dx times unit length. And at the other surface, at this surface, v dot n cap has to be positive because of the symmetry in the problem. So the velocity over here, so v dot n cap, if it has to be positive, the velocity here will be some minus ey, so that v dot n cap is aligned. Okay. As per the coordinate system, the normal vector is also minus ey. So v dot n cap is positive. So the velocity at this particular point will be u infinity ex minus v ey. So that the flux is still because of v ey, but the momentum in the x direction that is carried is still going to be u infinity. Now you may say, okay, so I should have some contributions in the y momentum equation as well. But no, because what is the y momentum carried at this surface? It will be rho v v dx at this surface, and at this surface it will be, okay, so what is the flux? It is still going to be v dx because v dot n cap is positive, but now the momentum in the y direction being carried through at this surface is going to be minus rho v. So these two terms cancel out because the integration is over the same length dx. So they will cancel out and you will have no net momentum across combined across these two surfaces, and that is obvious because the body is symmetric. So this should be obvious. So the velocity at this point, as he has correctly mentioned, is not going to be u infinity. It is going to be u infinity plus another component of velocity. And if I were to draw the vector diagram, it would be velocity coming in, velocity having a net reduction over here, and some velocity like this. Okay, and this velocity is combined of u infinity and u. Is it clear?
Yes.
But very observant question. I'm pretty happy. Pretty happy. So is the flow of the problem clear? You have to always make sure you first find out all the fluxes going out of the object of the control volume. If you cannot find all those volumes, you will be in big trouble, because in that case you will not be accounting for a certain momentum flux across the surface. Okay, so any other questions? So now suppose you are a sports engineer, and suppose someone tells you, I want to find out the force acting on a cricket ball, right? And there is a wind tunnel. A wind tunnel is able to create a uniform inflow, so there is air coming in, and you have very small velocity measuring devices called as anemometers. So velocity measurement device, there are certain kinds of devices, they are called as hot wire anemometer. Okay, you can find out the velocity using laser Doppler velocimetry also. There are various ways of finding out, and you move your anemometer at all points in the domain across very small delta y's, so small delta y's, and you will get a discrete velocity. So velocity over here, the anemometer will measure something like this, over here like this, over here like this, over here like this, over here like this, like this, like this. Okay, so then you interpolate and find out this shape, and because the seam position is not symmetric, I have drawn it slightly asymmetric as well. Because of this, you can then proceed to find out the net flux that is going to come out. But because you have disturbed symmetry, and because you have a hot wire anemometer ready at hand, you can measure the velocities over here as well. Something So you measure the velocities here as well. You interpolate the velocity. You interpolate the velocity. You find out all the fluxes. You first ensure that mass is conserved. Then you move on to momentum conservation and you find out the drag acting on the cricket ball. Very crude way of doing it, but hey, it works. And any observant student by now must also recognize that only a 2D thing will not be sufficient. You have to obviously do it in 3D. So you have to do all the measurements in 3 dimensions because the cricket ball leads to a flow disturbance in all the 3 dimensions. Okay, is it clear whatever we have discussed today?
Sir, I did not get that. How did you relate the y velocity and the u infinity at the top surface?
It is related through the mass conservation. The y velocity is responsible for mass coming out of the top and bottom surface. So u dot n at the top surface, so this will be essentially rho v dx times length on the top surface. This will be rho v dx l on the bottom surface. So hence I am able to relate the fluxes because of the y velocity at the top and bottom surface to the fluxes coming in through the other surfaces which are oriented along the x direction. Okay. Is that fine?
Yes, sir.
So great. Let me stop recording.
Sir,
Yeah.